Yeah, good afternoon, everybody. So it's an absolute pleasure to be here. And this conference, the way I've been uh, looking at things and just listening, it leads me to believe, I think this is what a lot of us are thinking about. How do we do research? How do we teach students? So this is just a very, very timely discussion. So if I can, let me share my screen or at least the slides. So this is just to give you a little bit information about my background. So I'm the Assistant Vice President for Research for Cyber Infrastructure. I'm the Director of High Performance Computing Center here at Oklahoma State. The other thing I also do is I'm a professor in Department of Physiological Sciences. I have a NIH-funded research program here. So in terms of the challenges for data research and educating the students, and this is something which a lot of us have been thinking about. So the way I would like to say this is several years ago, several decades ago, the way research was done was typically if you were an experimentalist, let's say a chemist or a biochemist, teaching students would basically mean teaching them how to do wet lab experiments. Everything was posed into a question, then you would go into the lab, and then you would actually do experiments. But in a matter of 20, 25 years, everything has changed how we are doing research. It's now driven by modeling in many, many domains, especially related to environmental research and climate. It is about modeling and collection of data. So every question you ask is driven by what data can you collect, how do you collect it, and what's the information or knowledge you're extracting from the large data sets. Um, Now, introducing students or even educating them in these domains basically means them is to teach them how to walk first, which is teaching them how to use the computational tools or programming as the first step. If you want to teach a student how to look at a large data set, it doesn't make any sense for them to start looking at a data set if they don't have any context of what those data sets are. Can they open these data sets and they can even process any of this? And this is challenging. So one example I would like to mention is that when students come into my lab, and not just students, we're talking about postdocs, it's a real challenge because as individuals, we don't understand the value of data. If this is data which is collected by the labs, and this is could be hundreds of thousands of dollars or millions of dollars, and students don't have the context, they can actually delete either by mistake or say, oh, you know what, let me just empty space. My disk drive is full. Let me just delete it. They don't realize that they can actually make uh, changes to the data set. And this is challenging. So I mentioned to my students that think of data as very expensive glassware. Be delicate with it. Don't play with it just because you can, but think of it. The first thing you should be doing is copying. Don't work on the concrete copy, authoritative copy. Make a copy. And if you cannot make the entire copy of the data, make a copy of the portion of the data that you will be working on. And teaching good discipline and good practices. The other thing I would like to mention is when students come in, one of the challenges I feel is they really want to just go to the last bit. They want to do the research. And sometimes I actually hold them back for a reason. I say you have to do the first thing first. You need to learn how to compile code. You need to be able to program before you can use the programs. And the discussion quickly goes to, well, this doesn't make sense. I should be able to download the program and be able to use it. But what I gently remind them is that garbage in, garbage out. If you don't understand what you are actually doing, then it doesn't make sense what you're going to get at the end of the day in terms of results. So for them to understand that be able, so one example is if a person just downloads a code which was compiled or developed in Python, let's say 2.7, and when the operating system is upgraded, the computer has changed, now the Python flavor is 3 point whatever, it doesn't work. And the student is completely clueless. So for me, it's very important for the student to learn that, look, this is how you compile code. This is how you actually run these things. And then everything will fall into the place. And this is an ongoing discussion. So these are the challenges of handling data. Now, the other bit which I would like to discuss real quickly is about courses. So everybody, including the students, understand that they need to have the right background and understanding of how to be able to program and look at computational modeling. But who should be teaching these courses? And this is a real challenge. Different domains require different tools and techniques. So it's not a one size fits all, that we can just teach a computational set of courses and say, okay, you know what, you'll be working in microbiology, doing bioinformatics. This is the same thing as being able to use uh, uh, the information in climate research. So who should be teaching these courses? The domain faculty, environmental research and climate change. The faculty does not necessarily have the time to do this and may not always have the up-to-date expertise to be able to teach these courses. So the proposed solution, which has been successful in many places, is to actually have shared courses. So the faculty from different domains sits down and says, okay, these are the core things. And you can always divide some of the courses into the basic requirements. You can actually have programming, parallel programming, scripting, high performance computing, and you can actually include this as a core set. And then if you want to branch out, if let's say the climate research is going to use a large data sets, you can actually look at handling things differently, NetCDF, HDF5. Uh, so you can actually branch out that may not be required in other places. One of the challenges that all of us has faced as educators and researchers is that the computing and computational modeling and programming, the material is so new. Every time I look on the web for with a new software tool, there's a new programming language. And I've just stopped tracking them because there's so many, almost I would say, one per month that I learned about. And when that is happening, the teaching material does not necessarily exist. So how do you address this issue? Because the material is in flux, the programming models are in flux, the programming languages are in flux. Python is so different. When I started programming, it was Fortran 77, then C, then C++, and now it's Python. And I'm hearing now there are another dozen which are going to be the latest and the greatest. So the opportunity I have, and this has been done successfully in many different places, the way to think about this is to have a center for data-driven discovery at OSU and other places where you have different people coming together, bringing different expertise, because we may not have the time and expertise to do this individually, but bringing together and developing a core set of classes and also research experience programs would be beneficial for the students. And the last bit is for the students to be successful in this domain and also related domains, uh, they have to get hands-on experience. So we can talk all day, all month about this, but what we need to do is we need to also give them hands-on experience. And where are these resources to be able to give the students the hands-on experience, whether it's the cloud or high-performance computing center or whatever the group resources are. Not all groups have resources, access to these resources. So we need to have a dialogue about being able to share these resources. The other bit very quickly I'd like to touch upon is that the technology, underlying technology is also changing, not just the programming aspect. The GPUs 10 years ago, they were new, but now they're so common. Now the CPUs are changing. So with the low power processor, the ARM processor, how the programming models will be developed is going to be drastically different than Intel or AMD processors. And this is something which will impact research in many domains. With that said, I think this is an opportunity, especially HBCC. My center will play a big role. What we are planning to do is organize a set of workshops in partnership with domain faculty. So this would cover multiple aspects here. We can cover the basics of high performance computing and also educate students about the technology as it stands today and where it could go next. So they can actually start productive research experiences when they are ready to take the research hands-on. With that, I think I'm out of my own time, so I'll stop here.
Very good. Thank you so much, Pratul. Just a reminder to everyone, please definitely use that Q&A function to ask questions of the panelists. And at the end, we should have plenty of time for additional discussion and questions then as well. But with that, I'm going to turn it over to Brian Murray. Brian is an assistant professor in natural resources ecology and management here at OSU. And specializing in forest ecology and geospatial technology. So, Brian, we'll turn it over to you.
Thank you, Kevin, and thanks everyone. I'm happy to be here and presenting. And I guess I'll see. Go ahead and share my screen real quick. I just had a couple of slides to share. So just a quick introduction. I'm an assistant professor in the NREM department at OSU, and Kevin said, can you guys still see the screen? Sorry.
Yes.
Okay. Yep, assistant professor in the NREM department. And I teach a couple of geospatial and GIS related courses, like our geospatial technologies for natural resources, which is sort of an introduction to geospatial, to GIS and a little bit of remote sensing. Our applications of geospatial technologies, which is a more of a hands-on learning course, and then a spatial and non-spatial database management course for natural resources that is for graduate students. And my research generally focuses on issues related to ecological resilience and other things related to spatial ecology. So in the classes that I teach, one thing, both here and when I taught in an environmental science program, many of the students who take the classes that I teach are generally more interested in working outside, or they didn't really major in natural resources or environmental science to use computational technologies. And so some of the challenges that I've had are just things like building the motivation, kind of motivating students to understand why this is important and why it's a really important job skill for them to master, and also just building confidence. I've had some students tell me that they're just not good at technology, and so trying to take that and build new confidence in being able to use the technology. And so I generally focus on, like I said, building confidence and providing a framework for learning new skills. We can't expect to teach really advanced, we can't teach everything in a single semester. So if this is the only course in geospatial technologies a student will take, like, how do I focus on helping them build a frameworks to make them into lifelong learners? And also, how do GIS specialists frame and approach problems? Like, how can they think about problems in a spatial context, even if maybe they don't come back to use the technology in the future? I think that can be an important skill. And so these are kind of difficult goals to have sometimes. And in my classes, I typically kind of start with some hands-on exercises where students can get start to learn the basics for the software first, but mix in some lab activities that are based on some things that I think that they're interested in. Maybe a lab involving data from forestry or a wildlife example, rather than just generic data, and kind of move that into problem-based learning. So once they've learned the basic tools, I introduce like, okay, well, you have this question that we need to solve. Like, how can you put those tools together to answer that question? And that is more towards the end of my intro course or in my applications course. And the applications course is basically developed as a service learning course where we work with partner with someone outside of the university to conduct a geospatial project in conjunction with them. And the scenario we create is that the students are basically a consulting firm. And so they have a lot of freedom in developing the project. So that helps with working through problem solving. But through all of this, it's really important to provide the right amount of scaffolding. So knowing, having the right, introducing the right concept at the right time, and not overwhelming students with information they're not ready for. And this is kind of with undergraduate students in mind. I also teach a graduate course in spatial and non-spatial database management. And I would say, in addition to the normal skills you would teach in that class, I have my grad students develop a data management plan. And I think it's helpful to know, to have that experience of developing a data management plan potentially for a grant proposal that they may be writing someday. And so just being aware of that. And I think I've had positive feedback from graduate students that understanding how to organize their data was something that maybe they didn't appreciate initially. I think it's something that a grad student, and many of us, are often interested in the question, and we kind of want to rush through that and not do a good job of organizing data. So in summary, these are some of the challenges that I've encountered and some of the solutions that I've found, but this is a challenging thing to do. So that's my presentation. And so thank you. Oh, and I'll do there we go.
Okay, well, we've got a couple of minutes for questions. If there are any questions for Brian right now.
I have one. I can't use the Q&A because I'm the host, so I apologize for that. My question is, you hit on something that I have discovered in all phases of my life and career, even as a parent, which is, trying to get students past the hurdle of thinking they're not good at it, and frankly, they're afraid of it. And so have you, do you have any insights about ways to do that as early as possible? Help them get past that.
I don't have, well, I'm not sure I have like a perfect answer, but I think that's where providing the right amount of scaffolding, like basically to not overwhelm a student with too much, asking too much of them or expecting too much early on. And so in some of my earlier activities in class, I try to do some activities that are more, try to build their interest in the topic, but not be too technical. And then it's kind of, I guess the idea is to kind of lead them into using the technology without really realizing what they're doing, and sort of appreciate the power of it. But that's not, I guess, not always an easy thing to do. So it's definitely a challenging topic. So
Any other panelists want to add on to that? All right, any other questions before we move on? All right, well, thank you, Brian. We'll look forward to visiting with you more in a few minutes during the Q&A session. Our next speaker is Jamie Jacob. He is a professor in mechanical and aerospace engineering and the director of the Unmanned Systems Research Institute. So they do a lot of work with drones and imagery and dealing with large data. So Jamie, if you want to take over.
Great. Thank you, Kevin. I really appreciate that and the opportunity to speak. I'll obviously be providing a perspective from the drone scenario, which is really looking at big data, not only issues, but also opportunities. And these are, some things for students to think about because they're going to be at the forefront of this transformational exercise that we're going to see over the coming years. Really exciting time in the environmental sciences to be able to use all these new tools to be able to get new data and observations. And if we look at it from the climate change standpoint and opportunities that climate scientists and atmospheric scientists are using now, it really goes back to providing an entirely different picture of what's happening in Earth's atmosphere. And traditionally, we've really been capped in terms of what we can measure, our ability to go out and essentially touch something in the atmosphere and get actual data from that, which is particularly important if we want to not only get data for weather, but also for climate. And as an example, if we're looking at weather measurements, those are typically limited to balloon type of measurements or things that we have on the ground. Now, of course, we've had satellites, and satellites provide a great visual detail of what's happening from the top down, but they're limited in both what they can see, when they can see it, as well as the types of measurements that they're able to get. There are just some things that you have to be able to touch to get accurate measurements of those. And so, what unmanned systems or drones are going to be able to do is provide us a capability to get data directly within the environment that we're operating in. So that way, that becomes a real useful enterprise for us. And we can kind of think about it in terms of a big data problem, because traditionally what we have is relatively sparse sampling, where we have small points that we're able to touch and get measurements from. But with the advent of these new systems coming online, we'll be able to get abundant sampling. And this is really starting to open up new opportunities where students can come in and think about things from a new perspective that haven't been tried before, because basically we tend to get set in our old ways of going out and taking measurements, where students will be able to look at things from a new perspective. And not be used to doing things the way that we always do them, and apply the new technology, really, which they're very used to from an early age, and figure out how to get the new data. And what's exciting about this is it gives us new ways to actually not only measure but also visualize, so we can start to see beautiful maps of what's happening within the different environs of the Earth. Not only the atmosphere, but also the ocean. So that way we can start to build up a picture of what's happening over time. In this example, just a kind of a standard morning in Oklahoma, where now we can see the growth of the boundary layer that we have in the morning as we start to see the transition from sunrise throughout the day, and see how that impacts the atmosphere. Now, we've also been using high performance computing resources to start to plan these types of missions. For an example, if you want to map out a large area around a severe storm, how do you go about doing that? Well, it's something very difficult to go out and test, because you don't have the opportunity just to fire up a storm and see what works and what doesn't work. But what we can do are use those high computing resources to be able to generate the environment virtually, and then virtually, fly or operate drones with it in the environment and see what works and what doesn't work. And again, this provides a great sandbox for students to think about in the future about how they can generate these virtual environments and try new things out. Oop, sorry about the sound on that one there. Now, this is not only focused on drones, which we think about in the air, but we're also doing this on the water as well, and that provides us the capability to map out things such as water quality and other environmental parameters that might be related to pollution or HABs or other instances that we might see species monitoring. And so we can do this in new ways and be able to get the data really in a fraction of the amount of time that we've gotten the data in the past using traditional resources. So the students now have to think about this in terms of, well, I can use these tools to get more data much quicker, but like was mentioned before, garbage in, garbage out. You got to make sure the data that you're getting is good and you actually know what you're going to be doing with it. Just having a lot of data by itself isn't enough. And this always brings me back to what I like to talk about is the hype cycle. This not only applies to drones, but any type of new robotic technology where we have some new flashy tool that comes about and we get into what we think of as the peak of inflated expectations, or this latest tool, or I like to think maybe the latest code. And I'll give a shout out to those of us that were steeped in Fortran 77 way back on, who still have to go through the process of trying to get caught up and learn the new latest greatest code to be able to keep up. But something else may come along that's better, or that product is not necessarily going to work like we expect it to. As we really start to put these tools out into the field and really test their limits, we fall into what is called this trough of disillusionment, and it takes time for the users to be able to provide feedback to the developers before these tools finally become productive. But what's really exciting about this is most of the students coming along are what we like to call digital natives, where most of us on this panel are really digital immigrants. We started to see digital technology come about, in a very gradual fashion, where now, we essentially have an iPhone or iPad from the moment that we're born, and we can start to, operate those, and that provides a very different mindset for those that have grown up with that capability. To start to implement, new ideas of how we use these technologies. And furthermore, things are just getting cheaper and cheaper. The ability to have microcomputing resources in the field, gathering thousands of points of data continuously, is only going to become more ubiquitous over time. So that way we'll have sensors everywhere that allow us to measure environmental variables. But like I said before, at the end of the day, we have to figure out what we're actually doing with that data. Just because we have it, doesn't mean that it's necessarily going to be useful, particularly in trying to understand something as complex as the climate, and turning that into usable data that we can then input into climate models. But drones by themselves are going to become great resources in terms of being able to pull data together. Here's one example. This looks like a kind of a blurry photograph of the library, but it's actually stitched together from hundreds of different images, which generates a full virtual capability for us to work and modify this model in a virtual environment, in a full 3D virtual reality that we can pull together. So we'll have lots of capabilities that will provide us really unique resources And I think it's an exciting time to be a student, to be able to start to pull these two different worlds together, these computing resources and touching data in new ways that we haven't been able to do before.
Well, I think we have a few minutes for questions. And Jamie, I'm amazed at all the work that y'all are doing there always. But how do you transition your students into being able to work with these big data sets and imagery? How do you onboard them, or do most of them come educated and ready to go, or do you have kind of a training program?
No, I think honestly we're probably not doing nearly as good of a job as we could be doing because it's still kind of an ad hoc process. I think most of this technology is so new and the capability to gather so much data that we're still in the process of learning as we go. And one of the issues is we have different fields that have different perspectives that are all coming together. I mean, as engineers, we tend to develop the tools, but we're also very interested in figuring out how these tools can be used to monitor the world around us. And so, kind of being at that intersection provides some unique challenges, that require students to be very creative and essentially lifelong learners, which I think is true for all of us here.
Mm-hmm. Well, sorry.
Do you see the questions in the Q&A, Kevin, or do I need to read those?
Do we want to take those now, Kay, or wait till the end?
That's entirely up to you. Perfectly fine.
Time, so I think we can take a few of these questions.
Okay. All right.
You...
Well, if you can see them, I'll leave it up to you.
Okay. The first question is, what is your experience with international students and how do they perform with the use of drones and large data sets, especially those who come from countries where the use of computer is still rudimentary?
Yeah, I guess I can take that. I think what we tend to find is most students of a certain age tend to do pretty well because I think everyone within the collegiate age group right now is still pretty used to using technology, computers, cell phones, smartphones from a relatively early age. So yeah, I don't think we see much difference, between the usability of those systems from international versus U.S. students. I do think that U.S. students still tend to have better hands-on capabilities in terms of working with the systems to be able to, the U.S. tradition of taking things apart and tinkering with them and putting them back together. But I think also we're starting to see that transition a little bit with the ubiquitousness of these small scale, very inexpensive microcontrollers, like Arduinos and Raspberry Pis, which, you can, buy for tens of dollars now across the world.
Excellent. The next question is very interesting. The question is, will big data analytics make scientific method obsolete?
I don't know who wants to take that one, but I think it's just quite the opposite. That I think the scientific method just even becomes more important because you have to have an understanding of what you're looking for within the data itself. And I know everyone likes to get on the machine learning bandwagon, where you're just throwing everything out there and randomizing stuff until hopefully you find some patterns. But the more data you get, the more difficult that becomes. So you really have to have physics start to drive things in order to understand what's happening, in my opinion. And I think that's an opinion.
Thanks, Jamie. There's one more, and then we'll move on to our next speaker. This one is, how do you strike a balance between subject matter training of students versus quantitative tools they need to do that research?
Yeah, and you know, one of the things that I found really useful are the carpentry tools, you know, that have been provided on campus. Those are really great resources that I can start to point students toward, because there's so much now for the students to learn that, you know, traditionally we don't cover in graduate courses, since they tend to be so theory based and not focused on really what I call developing skills that they can use for data analysis. So I think a lot of that, you know, varies from student to student based upon the research uh, um, project that they're working on. I know. So the follow up question was the carpentry tools. I don't know if those are covered elsewhere within the CADRE conference, but I assume those have been talked about in some of the sessions. And that may be a question for Kay to answer on the carpentry tool side.
I will drop the answer in Slack.
That's perfect. But I think that's one of the great things about OSU that I found is the development of those opportunities for students to be able to use those carpentry tools in the courses.
Great, thank you, Jamie. Our next speaker is Phil Alderman. He is an assistant professor in Plant and Soil Science Department here at OSU, and he focuses on ag systems modeling. So Phil, I'll turn it over to you.
Sure thing. All right, I will assume that you can see it. If you can't see it, let me know. So thank you for the opportunity to share from my perspective, working in the area of agricultural systems modeling. What I would like to do is just to give you a quick intro to what I mean by that. And then I want to walk through an example of a student's project that I'm working with this student right now. And through that to give just an example of some of the skills that are needed for that project, just to illustrate some of the challenges of doing this kind of research, and then the vast array of different relatively specialized skills that are needed to even solve something that you would think might be a relatively straightforward problem. So what do I mean by agricultural systems modeling? Well, when I think of a model, I think of it as an approximation to the real world that helps us learn something useful about how the real world works. And so there are a number of different types of models: statistical models, numerical models. When I talk about agricultural systems models, they're systems of differential equations that describe how an agricultural system changes over time. So what we're doing here is not a static model. It is a model that's trying to reproduce, or at least mimic, the behavior of an agricultural system throughout a growing season, for example. And so what that might look like is that you start out with a crop that's growing with very little biomass. It's sort of growing throughout the season. And this is, think of winter wheat. It's growing very slowly during the winter season. And then temperatures warm up and you have biomass accumulated at a much more rapid rate. And then at the very end, you'll see it sort of level off as it approaches maturity and it stops growing. Okay, so what we're doing is building models that essentially mimic this behavior of accumulating biomass over time, producing yield of various sorts, which will be different for different crops. But that evolution of the system over time is what we're targeting with these types of models. And so the example problem that I'd like to illustrate is this idea of, okay, what can we do to adapt an existing crop model for wheat for predicting statewide dual-purpose wheat production? So what is dual-purpose wheat production? But in Oklahoma, this is a very common practice that producers will plant a field of wheat, and then during the winter months, they put stocker cattle out on that wheat to graze it, gain weight. It's a very high quality forage. And then at the before a certain developmental stage, they'll pull the cattle off and then allow the wheat to then recover from being grazed. and to eventually, go through the rest of its life cycle and produce wheat grain for sale. And so, you might think, okay, well, you've already got an existing crop model. You just kind of need to run it and maybe tweak a few things on it. Maybe that's a relatively straightforward thing to do. And maybe at a conceptual level, that's true. The legacy crop model that we're working with is coded in Fortran. It's a mixture of Fortran 77, but now most of that's been brought over into a more modern versions of Fortran, Fortran 90, and some of the 2000s, some of the later standards make it a little bit easier to work with. So for those that we're talking about, Fortran 77, it's still used. It's still a part of the code bases in various fields. So in some ways, if you're going to take advantage of that legacy code, you have to get familiar with some of these languages. Even Fortran, it's still needing to be taught, or at least have students learn enough of it to be able to modify code, even if not writing things from scratch. But this Fortran is a compiled language, and so what that means is that you don't just write the code and run it. You have to have a compiler and have a knowledge of how to use compilers to pull that source code together and package it into something that can actually be run on a computer. So in addition to knowing the language of Fortran enough to be able to make whatever modifications that are needed, you have to be able to compile that into something that you can actually run on your computer. Well, beyond that, we have all sorts of, when we're thinking about a cropping system, weather data is very important. We have temperatures that are affecting how the crop grows. We have rainfall that's falling and influencing soil moisture, which is affecting how much growth we have. And where do we get the weather data from? Well, they come from different providers. In this particular study, we're using weather data from Mesonet. And Mesonet has their own specific, unique file structure for storing the weather data. And so we have our code that was developed to be able to read in that format and compile it and put all those weather data files, which are at a certain time interval, and patch them together to have what we need to be able to run the model. Once we have it imported in, we then need to convert that into text files that work with the crop model, the particular crop model that we're working with. So it's a specific format coming in and a specific format going out. And we have had to develop our code to be able to facilitate that process. We get to soil data. Soils are very important for being able to grow wheat, and understanding how different soils provide different nutrients and different water holding capacities and things like that. Very important for being able to get accurate soil data. The NRCS provides a soil data access server that we can query, but in order to access those data, we need to know SQL, structured query language, to be able to put together queries to pull the data that we're interested in. And then we have our code to be able to pull that in and package it. And again, once we pull the data in, we've then got to reorganize it and generate some output files that are relevant to the crop model that we're trying to work with. If the soil data that we get aren't exactly the right variables that we need to run our model, we often have what are called pedo transfer functions, which are mathematical models for being able to translate things like the clay content, sand content, silt content, bulk density, different properties of the soil that are more commonly measured, and convert that into other parameters which describe how those properties affect the soil water holding capacity of a soil. And so we've had to bring in some Python code that was implemented to do this pedo transfer function capability. And so we've got data coming in from the Surgo database. We shuffle that over to Python for generating some outputs. That comes back over to R, and then we write our soil input files that can be read into the crop model. Now, when we're doing something like trying to generate simulations across the whole state, we're talking about thousands of data points and grid points across the state. And to do that in an efficient way, we want to be able to run each of those simulations in parallel rather than waiting one to follow the other, sequentially. And so we are using the message passing interface called MPI, which is used to spread out and distribute the simulation of all of those different grid points across the whole state. And once we have code that can work that way and can work in parallel, we have to be able to run it on a supercomputer, a computer that actually has all of those different cores that we can distribute all that work to. And so we have to be able to know a little bit of Linux shell scripting, and Slurm is the sort of the job manager that we use at the OSU High Performance Computing Center. So that you have to be able to describe, well, what is needed for being able to run these simulations? How does that work? And so there's an additional set of skills. And then once we get all of that output, now we've got all these grid points. We need to figure out, okay, how do we make sense of this? And how do we manipulate those model outputs in a way that allows us to tell a compelling story, to understand what's going on? And so we've got a mixture of our code and some interfaces to GIS libraries, like the GDAL and several other geospatial analysis libraries that allow us to manipulate those model inputs to generate sort of maps of yield and other variables across the state, and allow us to understand what's going on. So when we think about all of these skills, and this is just one student's project, this doesn't even, there are other students in my group that are working on projects that are similar but have different wrinkles to them, and there's a whole other set of skills that are required. But even in just this one student's project, we've got compiled languages, interpreted languages like R and Python, a knowledge of SQL, which is sort of interacting with formal databases, dealing with parallel programming and all of the challenges there, and then dealing with geospatial analysis. So even something that might on its face seem somewhat straightforward very rapidly turns into a whole set of skills from a lot of different domains that are needed to be brought together to be able to solve this one problem. And so this is just one example. Again, like I said, I've got other students in my working in my group where maybe 70% of the same set of skills are required, but then there's another 30% that's something entirely different. And so because of the number of different dimensions or sort of sets of skills that are needed, there is a real challenge to being able to, there's no course on campus I can send them to learn these things. There are bits and pieces where I could send them, but half of their coursework would be going and taking a class in NREM on the geospatial and GIS modeling. And there would be another course possibly offered by the HPCC on Python and parallel programming, and another one related to R coding. And so half their graduate program ends up taking courses in other departments that are just teaching skills that aren't even related to their domain. So one of the real challenges, and this was one of the questions raised just a moment ago, is if we do set aside time within the curriculum to address some of these skills, does that push out domain expertise that's also needed? I was having some interactions with some of my students recently, and I realized I've done a poor job of, I haven't done as good a job as I should have on emphasizing the connection between crop physiology and the models that we're using. So that domain expertise, that knowledge of crop physiology and how that plays into these research questions, there's a gap. They've been spending so much of their time within their graduate program trying to get a grapple with all of these technical skills that are needed to complete their project, that they have not been able to invest as much time getting back to the actual fundamental research questions from the domain perspective. What does it mean, for wheat to grow under grazing in Oklahoma? because the students been spending all of their time thinking about, well, how do I get this data into this format and this data into that format, and then put them together and then push them through the model and get, all of those technical details end up consuming so much of their time. It's very easy for them to lose track of that bigger picture and the actual original research question that we set out to address. And so anyway, I thought that this is a really good example of some of the challenges, when we have all of these different areas that have to be addressed in a technical sense, and how that can often sort of displace or at least cloud out that domain focus if we're not careful. So anyway, I'll stop there.
Thank you, Phil. I really like that last slide of yours that really listed out some of the skills. Maybe when we're done, I'd like to talk about, is there overlap between the different disciplines on some of those key skills? I expect R and SQL and Python and maybe others would be consistent skill sets that would be needed and required across the different disciplines and groups. And maybe areas that we could focus future educational efforts on, both at the undergrad and graduate levels. But thank you for all that, Phil. We'll move on to our last speaker and then get into our discussion time. But our last speaker this afternoon is Jackie Vajunik, and she is a professor in geography, and I understand that she's just getting back from a stint with NSF. So Jackie, look forward to your presentation.
I'm coming at this from a bit of a different perspective. I'm a muddy boots geographer, and I just came back from NSF. So I'm thinking about this in a more philosophical way and a more meta type of way. Right. So coming from NSF, I'm always, where's the money? Follow the money. Well, one of the big 10 ideas is harnessing the data revolution. And this is really about, creating data-enabled futures and teaching students how to deal with big data. So that's one of the big ideas. And another one that I think is really important for the discussions we're having right now is growing convergent research. And when I talk about convergent research, explain it as transdisciplinary plus people, plus citizens, plus businesses, plus other people at the table, because this is how we solve complex problems. And most of the way that is wrapped up at NSF right now is coming from basically these ideas, and a lot of these other ideas overlap those two ideas. So there's a lot of entry points where I think environmental fields can get involved with research at NSF. And all of the things we've been talking about, these new spatial data sources, drones. One thing that I'm really interested in is geospatial privacy and VGIS type of issues with citizen science and ethics, machine learning or AI. All of these issues about data and thinking about the future of data and doing convergent research and making a student, developing students that can do that type of research, that can work with the social sciences. This is the nexus of environment and humans, and that human piece is really important. So things like data revolution, the future of work, convergence, human, environmental, geographical sciences, dynamics of integrated socio-ecological systems, sustainable regional systems, navigating the new Arctic coastlines and people, signals, they are all operating at that nexus. They all include big data, and they all need that human environment piece from a convergent standpoint. So this is how I think we need to be training our students, because this is where the bulk of the money is at NSF at this point. Okay, so going to the challenges, that was the opportunity. So the challenges, and this is my muddy boots perspective. How big is your N? Mae West once said, "Too much of a good thing can be wonderful." This seems to be the sentiment of the times, especially in geography and related environmental fields. During the first week of class, I presented some data on a payments for environmental service program in a small community in the Amazon. A grad student raised their hand and exclaimed emphatically, "But your N is small." It was true. My N was very small. It was 40 households and a single community. However, there were less than 80 families in the community to begin with, and even less were involved in the payments for an environmental service scheme for that matter. Further, the households were randomly selected and the small n stats were statistically significant. So permitting me the ability to generalize here and sound may be outdated, I am a Gen Xer who doesn't trust anyone. Perhaps I watched too much X-Files growing up, but large N data sets are easily available on the internet, and they've made a lot of my graduate students scoff at the idea of small N ethnographic fieldwork. At the same time, I know how my data was selected and collected and analyzed. My graduate students suspicious of mixed methods approaches are often very happy to get all the data they need off the internet in increasingly massive quantities. But I teach a required field methods course. It's a mixed methods course. So students can get their data off the internet, but I also make them go to the field. They often go kind of beingly, but they often realize while they're there how important fieldwork is to verify the results, whether it's remote sensing, GIS, or any type of spatial data. Ethically, I believe when we interpret data that can have implications that are either positive or negative on it, we need to see for ourselves. This is what Kant dared us to do, dare to know for yourself based on your own senses. This was the call of the enlightened, this is the call of science. There's a danger of allowing big data to become the new religion, and I think we need to teach students about some of these ethical issues. So I'll give you an example as a remote sensor. In the case of remote sensing, those of us who do it know that land use, land cover change categories are far from clean, crisp boxes being culturally created, constructed, and understood. Researchers, we have an ethical obligation to understand these differences. So anthropologists and geographers like Joel Wainwright or David Salisbury illustrate the power of remotely sensed deforestation maps to tell the story in terms of the person in charge, right? So the remote sensing analysis can prove what the person holding the power wants to prove. So for instance, this is a small 2-acre plot of subsistence farming. Is this traditional Sweden agricultural system deforestation? Is it part of a larger agroforest that's continually in use and going back to forest? Or is it something else? The answer really depends on who you talk to, what their agenda is, and who has the most power. These are kinds of issues that make an important case for the importance of co-produced knowledge and the importance of sort of being leery of all the data we can access on the internet, including remotely sensed data. It's relatively easy to hide behind the power of a large N. Dennis Wenger, a retired program officer that dealt with risk hazards, infrastructure management, and extreme events, once asked, do we really need more Twitter data? Are 4 million tweets really better than 1 million tweets? And more importantly, who's left out of the sample? I believe we have an ethical obligation to be more transparent about the data we're using, the potential bias, accuracy, and replicability issues, instead of hiding behind the power of the N. And I think we need to have these discussions with our students and train our students in this. I'm not saying we should avoid the use of big data, but I'm a huge fan of the scope and limitations section, which a lot of people are reluctant to acknowledge. So here's an example of, I think as a land system scientist, in the early 90s, we talked about metadata issues. We are still having these issues. All the time I get graduate students who pull data off the internet, there's no metadata attached to it. And when it comes to geospatial data, that could cause a slew of problems. And so I don't think we've dealt with metadata issues, but there's also data issues. This is an example of the EWG working group data. I had a student who scraped it off the internet for us. When we got it, it looked a little cattywampus. Then I had a student who I paid as an RA to actually manually cut and paste this data in. It still looked a little cattywampus, but in a different way. And if it wasn't for us in the field for 10 years in this area, we would not have been able to make sense of this data. So I'm making a case for the importance of field work, regardless of the data you get. So talking about the ethics, geospatial data from VGIS, crowdsourced or citizen science approaches is increasingly popular. It allows us to achieve large data sets for relative costs while democratizing science. These are all good things. However, we really need to consider transaction costs, and we need to train our students to do so as well, because everybody sort of jumped on the geospatial bandwagon. From a science perspective, how do we ensure the quality of the data collected? What are the inherent biases of self-selecting group of participants or data collectors? What are some ways to account for these issues? How do we balance the benefits of the known and the potential challenges? And how do we ensure that the human subjects are protected and not exploited? So this is an example of Forest Watcher. I had a million examples of these, but I deleted them. But anyway, this is an example of Forest Watcher. It's a citizen science app which monitors deforestation in real time, and it encourages curious citizen scientists to go to the location and figure out what is going on. This is great for biodiversity. This is great for people who are interested in deforestation. Yet across the world, forest watchers of various kinds might unknowingly be putting themselves in danger as much deforestation occurs in places of conflict. On the other side, marginalized and traditional people, like that example of the Swidden agriculture, have historically fought for their right to practice small-scale, sustainable Swidden agriculture, which is illegal in lots of places. For the record, this app has been used by sheriff's offices across the Amazon and has led to arrests. So what are the implications of seemingly spying on some of the most marginalized groups to begin with? We may have started out with an ecological study, but there's real human impacts here. Here I'm reminded of Foucault's Panopticon and power relations. Watch the watchers themselves. So why does it matter? This is one of my favorite photos from out in the Panhandle. Politics aside, there are often reasons why researchers aren't trusted in communities. If we are to involve people in our work, we can and must do better. For this reason, we need to train students to do co-produced research, to do community engaged research, to get involved with people on the ground, to make for better results for all of us with, to solve these big, complex human environmental problems. Otherwise, we end up with this kind of tension. And why does it matter? Because for every pixel or geospatial piece of information, there's people attached to it. So these are social and environmental justice issues for me. All right, so my conclusions, I really hope to make a case for mixed methods here. I think we need to train a new kind of student that could work across the social and natural sciences, to do co-produced research, to work with people on the ground, to consider these issues that are also ethical as this data comes out. A lot of times data, even if it is public information, once you put it into that GIS database or make it geospatial, put it all in a nice platform, all of a sudden data that was seemingly innocuous is now very sensitive. So I see sort of important ethical conversations that we need to have with our students. And I think we need to kind of think about what is the future, that kind of student we want, and that is needed for these types of complex problems. How do we train people to do convergent research? Thanks.
Great presentation, Jackie. It was very interesting. Let's open it up for questions from the participants as well as from the panel. Well, I've got some, so if nobody else does. So, as I'm hearing everyone talk, I keep thinking about maybe the need for maybe a certificate program that could cross disciplines and provide some of those key skills. It might not get every student to the point that they need it for every single program and dealing with all the different data sets, but back to Phil's skills list, the need for R and SQL and Python, and then to Jackie's point, data quality and data ethics. Seems like there's some key cross-cutting skills and understanding that needs to be conveyed out there that would then benefit, all the different users, data users across the university. So Pratul, I didn't know, and Kay, I know both of y'all do workshops and things like that, but has there been talk of maybe a certificate program, or has there been an effort to organize these student data education efforts more broadly across campus?
So I'll jump in. There actually is a certificate program. It's administered by the grad school, and it's called their 360-degree program. It is not strictly data skills. It's, in fact, it's all the things that grad students need, everything from, professional skills, writing skills, and so on. The carpentries is one of the things that, along with all the other workshops, the Data Bytes workshops and so on that we offer, are part of that certificate program. But I'm going to be a little bit of a devil's advocate and say that although I certainly think that fills a role, but it tends to be, preaching to the choir. The students that jump in and do that kind of thing are the ones that are not afraid. They don't have those fears of trying new things and being exposed to this kind of thing. And it's still good, but my own bias is that the best thing we can do is find a way to introduce students just as early as possible. We don't have a lot of control over elementary school, high school, etc. But if it's your kids, maybe you do. Maybe you can have some input. But we certainly have some input with regard to undergraduates. And so that's something I've been trying to kind of do a little bit of getting off the ground. And I see Nicole was on here, but I think she must be, maybe she's stepped away. But anyway, yeah, that's one of the things that I think is critical, is finding a way to, and I think Brian's the one that used the word scaffolding, and just expose them to this stuff as early and as often as possible in bite-sized pieces. And I will stop.
So among other challenges, one of the big challenges is to have such a program which is up to date and also appeals to, let's say, specific research domain. You have to have a program which appeals very broadly. So not just the few graduate students. So if you're going to only tailor this program to, let's say, 3 or 4 students per year in a specific program, it's not going to survive. The good thing about what we have been discussing in the last hour is that data, it cuts across many, many domains. That's great. On top of that, if we start thinking about undergraduates, when they're going to go into workforce, we wish many of them become researchers, but we know that's not the reality, only a small fraction. So the remaining ones, they should also see some incentive to take these courses. And I think we need to tailor-make these programs saying, okay, if you're going to go work in oil and gas industry, if you're going to go work in, let's say, e-commerce, all these tools that you will be actually exposed to these programs are still relevant for getting jobs in different industry. So I think that's the way to think about this, having, I would say, multi-pronged approach. So clearly the main arm is going to be a set of courses which is broadly applicable. But then if students are interested in saying, okay, what kind of job can I actually get when I graduate? We should also cater to that interest. And on other side, we can actually make specific courses for advanced research. And I think that's when we can actually get more traction at the graduate level, or even at, let's say, senior level undergraduates.
If I could chime in, I do see an opportunity for having possibly some core coursework which has some of those key skills being addressed in it. On the other hand, what I find, so I teach a class on, it's called Data Science for Agricultural and Natural Resources. So it's, the idea is trying to make available some of the tools needed for understanding data management, quality analysis and quality control, being able to do, manipulating different data formats and bringing data together from different sources to be able to not just have field data, but augment field data with other data sources, things like that. And what I find is that when I teach the skills just as skills with the sort of cookie cutter examples, the first go round, they get it enough to be able to complete the assignment. But where they really learn it is when they're working on their semester projects, where they're applying those skills to their thesis or their research project. And so I think a key aspect of whatever would be some sort of core curriculum would be needing to incorporate an element in which students are not just being taught skills in general, but that they're being taught the skills that are needed to analyze or manipulate data that's of relevance to them. And I frequently interact with students who took the, two semesters of statistics and still don't know how to apply it to their analysis. And so, it's like there's a danger of having core courses that everyone's required to take if we don't also take care to make sure that we're giving them opportunities to, or in some ways forcing them as they're learning those things to apply it to what they need it for. Otherwise, they go through the course, they learn enough to pass the exams, and then a year later or 6 months later, when they actually come to analyzing their data, they go, oh wait, I vaguely remember something. Can you explain that to me again? And then I, as the advisor, am having to, hopefully it's easier, but I end up having to, review, basic statistics. It's like, you took the class, what, anyway, so I guess I just wanted to sort of mention there is a tension between having something that's sort of generic, but then we also need to make sure that there's something specific. So I'll yield to Jackie. Looks like she has something to say.
Yeah, I guess I'm probably the generic one in that I think the skills are important, but real skill, because you could have the skills, but it's that getting people to leave their disciplinary baggage and methodological bag at the door and problem solve. That itself is the biggest skill. And that, I think, the thing that we still need a lot of work on. And that is where all the money is if you're just looking for research funds. But whether you're continuing on in academia as a student, that training that person who could be open-minded, do open-minded science, that's the place to be. But also, if you're going out into the world and having a job, what job doesn't create, like, where an example where you have multiple people trying to solve different problems and you're interacting with people? That is the skill that I think we need to deal with. And we've got, you have an NSF program like the Future of Work. Our work landscape is even changing, and so the way that we're interacting. So these are the kinds of things I think we need to think about, is how do we train the students that can do convergence both in the classroom and out of the classroom.
Yeah, and I'll just add, I think, one of the things that I found really useful, or most useful, is some of the courses that my students have taken that have benefited their research plan the most have been outside the department, and some of those outside the college. And we tend not to have enough capability at the graduate level for cross-collegiate coursework for the students. Not only do they, not really know about the opportunity, it tends to be outside their comfort zone for them to go, oh, I'm going to go take a course over in arts and sciences or in NREM. Engineers, it's almost verboten in that sense. But I think, having courses that they take over in geology, for example, have been some of the most useful, for their particular research projects. And that's where I think, going back to your original question, Kevin, a certificate-like program, or at least having that opportunity for students to take courses and get some credit for that somehow, because they tend to be so regimented, based upon what they're required to take, and just looking at the bare minimum to be able to graduate.
Yeah. We are out of time, but this is a fantastic discussion that needs to continue. As we look to the future, this is our future and the future of our students for sure. So we need to best prepare them. And without offering some of these core courses and getting more students involved in data education, we're not going to prepare them for the future. So this is something that I hope we can continue